Hey there, welcome to Pomodoro Joe for Saturday, October 21st, 2023. Today we're looking at LeetCode problem 1425, constrained subsequence sum. This is a hard problem. So, we are given an integer array, nums, and an integer, k. Return the maximum sum of a non-empty subsequence of that array, such that for every two consecutive integers in the subsequence, numbers index I and numbers index j, where I is less than j, the condition j minus I is less than or equal to k is satisfied. A subsequence of an array is obtained by deleting some number of elements, can be 0 from the array, leaving the remaining elements in their original order. Okay, so what this is just saying is we have some integer array, nums. We can go through and select a subsequence of nums, meaning we can select certain elements from nums. They have to remain in the same order, but we're allowed to ignore some elements. So for example, in this one, we've got these negative elements. We can ignore those as long as any two consecutive elements in our subsequence are within k elements of each other. So essentially, we just need to make sure that no two elements in our subsequence are more than k elements apart in their indices. All right, so let's look at the examples really quick. Example 1, 10, 2, negative 10, 5, and 20 with a k of 2. So we can have 10 and 2. Then we can skip the negative 10 because we can bridge that with 2 and 5. It's within two elements. So 10, 2, 5, and 20. So that's going to be 37. All right, that works. Now let's look at example 2. Negative 1, negative 2, negative 3. Now we have to have at least one element. So we could have negative 1 plus 2, negative 2, which gives us negative 3. Well, we're looking for the maximum value here. So the maximum value we can get out of this is just having one element of negative 1. And that is our answer. All right, example 3. 10, negative 2, negative 10, negative 5, 20 with a k of 2. So it looks like we could do 10, but then we'd have to do at least one of these two, negative 2 or 10. So we could just have 10. We could just have 20. We could have 10 minus 2, and then we could maybe bridge that with this minus 5, and then add the 20, so we could skip this negative 10, so we could have 10 minus 7 is 3, and then we bridge that with the 20, so that gives us 23, and that's our answer. Okay, so let's put 25 minutes on the Pomodoro timer, and we'll get started. Now, there are lots of different ways we can do this. One way is to basically go through, and for every element in our nums, we could branch and say, well, we either include this element in our subsequence or we don't. So that means for every element, we have two choices. We include it or we don't. So for every element, we actually split our problem into two subproblems, which means that we're doubling our problem every step along the way. So that is an O(n) squared algorithm. Every step, we're splitting the problem into two additional problems. And that's going to be very expensive. So let's see if there's a better way to do this. All right, so we've already seen problems like this in the past. So let's build on some of that knowledge to see if we can solve this problem. Now, one thing we've done in the past is to go through every element in our array and consider that element as if it were the last element in the solution subsequence. So for example, let's just go through all the elements in nums. For each element, we'll say, what if this is the last element in our subsequence? What is the best answer? What is the best subsequence that makes this element the last element, or that includes this element as the last element? Well, for that, we just need to look at this element and look back at the previous k elements. So the elements that lead up to this element, and we can look at those elements and say, well, what's the best subsequence that ends at those elements? And figure out which one of those gives us the best answer. So again, we'll just go through all of our numbers and consider each number as the potential last element of our subsequence. If that element is the last element of our subsequence, then we can add it to the previous subsequences that came before. And for that, we look at the last k, or the previous k elements, so the k elements that came before this element, and we can ask the same question. What is the best subsequence that ended at that element? Now, of those k elements, one of them will have the best answer, or the maximum answer. And so we can add our new element to the end of that subsequence to give us a new subsequence. So we'll be doing that. So we'll start with some result. Now we have to have at least one element, so I'm just going to use nums at index 0 as my basic answer. So that's our result to start with, and we will return our result at the end. All right, now we're going to go through every number in our nums, and we're going to consider that number as if it were the last number in our subsequence. Then we'll find out, well, what's the best subsequence to add that number to in order to give us the best answer. So for every I in range, now we've already got 0 covered here, so I can go from 1 to nums. Well, let's just go through 0. It'll be easier. So for I in range length nums, let's build a helper function here. So this option will be our helper function. So max subsequence ending at this index I. So we have this helper function. What's the max subsequence that ends at this index? That's this option. Now we just choose what's our best option. So our result will equal the maximum of this option or our current result. And then we return the result at the end. So that's pretty straightforward. Going through every element. If this element is the last element in our subsequence, what's the answer? What's the best option we get for that? And then we'll just find the best option of all of those options. So now we need to create this function, max subsequence ending at this index. All right. So what's the max subsequence that ends at this index? Again, our initial result will just be the value at this index. So let's see, this result will be nums at this index. And again, we'll return the result at the end. So what are the options here? So there are basically 2 categories of options. The first option is we just use this element as the subsequence. So we can just use this nums at index and return the result. Just say, we're not going to use any other elements. This is the subsequence. The other option is we add this element to the end of some previous subsequence. Now the only subsequences that we're allowed to add this element to are the ones that end within k elements of this index. So they have to have ended before this index, but not before this index minus k. So for that, we'll just say, let's actually do this. Let's have a window. So our window start, well, that's going to be this index minus k, but we don't want to go below 0. We don't want to be out of bounds. So that's if this index is greater than k. Greater than or equal to, I guess. Otherwise, we'll return 0. We don't want to go below 0. What about the window end? Window end, well, that's just going to end at this index. So that's pretty easy. So we have this window that goes from this index minus k to this window or this element itself. All right, now for every index, I'll just call it I, in range from window start to window end, so now we'll just look back and say, well, what's the best subsequence that we can get that ends at this index I? So that's this option, and that's going to be, well, we'll just use this function to find it. So what's the max subsequence that ends at this index? All right, and now our best option will just be the maximum one that we find so far. So we'll just say max of this option or our current best option. Okay, so now we find the best option that we can use, the best subsequence we can add this element to. Now, we only want to do this if that subsequence is a positive value. If it's a negative value, we might as well just use this element by itself. There's no point in adding a negative weight to this. So our result here will equal result plus this best option. So we're going to add our result, this current element, to our best subsequence that we found that came before this, but that's only if our best option is greater than 0. Otherwise, we're just going to keep our current result. All right, now I could change this a little bit, make it a little bit clearer. So our result will just be this element plus the best option that we found before. If we have some subsequence that is a positive subsequence that came before us, otherwise we're just going to return this element. All right, so let's do this. Cool. So I think this is it. We're just going to go through every element in our nums. We're going to say, if this is the last element in our subsequence, what is the max subsequence we can create that ends at this element? Now to do that, we're just going to go through and look at all the elements that came before this element and find out which elements are valid within K and what is the best subsequence or the max subsequence that ends at that element. We'll just choose the best one. All right, now this is going to be slow, so I'm going to add @cache here. All right, let's run this and see how we do. Let's see, best option, reference before assignment. All right. Gotta create my best option out here. So my best option so far will just be 0. So I could add 0 to this. Actually, if that's the case, then I don't need this special condition here. Cool. Yeah, so we'll start out our best option as 0. So if the best option is 0, meaning we didn't find any subsequence that is better than 0, then we'll just add 0 to our current number. All right, let's try that. All right, seems to work. Let's see if we can pass all the tests. Time limit exceeded. We did 20 out of 36, so we're okay, but not great. Let's use this test case, and let's see if we can speed this up. All right, so there are a couple things we could do to speed this up. The first thing that comes to mind here is this for loop here. So this for loop is essentially running through K elements, looking for the best answer, looking for the maximum subsequence that ends in those K elements. Now, once we find the max that ends in those K elements, we're sliding the window by one step, and we're going to run the same for loop again over K elements, which are mostly the same. There's only going to be one element different from the previous window, the previous time we ran through this for loop. So what we could do is actually keep our window itself as an array. So instead of making all of these recursive calls, we could have an array where the index maps to the end element and the value at that index maps to the best subsequence that ends at that element. Okay, so let's do that. Let's create an array here. I'll call this the window. And so the window will just be an empty array to start with. All right, I'm not going to call this window. Because I'm not just keeping the window elements, I'm going to keep all of the elements so far. So I'll call this essentially max subsequence ending at array. Let's see, max subsequence ending at index. Okay, so this is very similar to our function name, but this is going to be essentially what we're using instead of our cache. So we have this max subsequence ending at index, and it's an array, it's a list. So when we check the value at that index, it will give us back the best option for that subsequence ending at that index. So we don't need this cache anymore because this is essentially going to act as our cache. Let's get rid of that cache. Okay, we'll still calculate our window, but now this option here, instead of doing a recursive call, we'll just look at our value here. We'll just say, well, what is the max subsequence ending at this index? And we'll pass in our index. But that does mean that we'll need to add our value to this array when we get our result. So the result here will need to be added, append to our array. All right. So it's a little bit confusing, but basically instead of doing this recursive call, we'll make the call one time. When we find the answer, before we return, we're going to put that answer into our array here. So for example, we pass in 0. We'll go through this. We'll come up with an answer. This for loop won't really run because our 0 won't go anywhere. It'll go from 0 to 0. We'll get our result, and then we'll append that result to our max subsequence ending at index. So for index 0, it's going to have this result. For index 1, it'll have the 1's result, so on and so forth. Oh man, I'm running out of time. So let's do this. Let's just see if this works. Okay, so this is still too slow. And a big part of that is this for loop here. Every time we call this function, we're going through basically the same window. It's only off by one element, trying to find the maximum element in that window. Now, we're shifting our window just one element at a time, looking for a new max element each time. There's probably a better way to do this. Is there some data structure that we know of that will keep track of our maximum values as we push or pop elements out of this window. Now, if you answered we do know this and it's a heap, then you would be right. So we can use a heap here. So what a heap will do is act like a bag of elements. You can put elements in the heap, but it will bubble up the minimum, or in our case, maximum value to the top of the heap. Then you can pop elements out of the heap, getting the maximum value each time. So when you put an element in, it sort of automatically sorts it. Every time we add one element, it will do a very quick insert. It will do that sorting for us, and we don't have to go through every element every time to try to find the max element. All right, so let's convert this max subsequence ending at index from just a list to a heap. And that's pretty easy in Python. So in Python, the simple thing to do here is instead of just appending, we will use the heap queue library. So that's heap queue, and we will push, or it's actually heap push. Now we pass in the heap. That's going to be this max subsequence ending at index. And then we pass in the value or the element that we want to store in the heap. So in this case, it would be result. Now the problem that we're going to run into here, though, we have two problems. One problem is the default heap in a Python heap will be a min heap, meaning the minimum value will be at the top. So one way to get around that is to invert this value or set it to negative of what it should be. And that will bubble the maximum, or it'll still be the minimum value to the top, but then we flip it around again and it becomes the maximum value. Oh, we're down to only 1 minute. I'm not going to get this done in a minute. I'm just going to speed through this. I'm not going to explain super well. I'm just going to run through. So we can't just store the value. We need to store the negative value. To convert this from a min heap to a max heap, we'll have to flip it back around when we pop these things out of the heap. So we'll heap push this value. Now we also need to know what index this value came from, because we need to make sure that this value is within our window. So let's not just store only the value. We need to store the value and its index. So let's see here, we'll make a tuple. We'll store the value or the negative value and the index where we found this value. So that's index. Okay. Now this window, we're not going to use this window anymore, or this for loop. We'll still use this best option. So let's, oh, time is up. All right, I'm going to keep going. So I'm going to go really fast here. I apologize in advance. So now that we're storing our result and our index as a tuple in our heap, so when we look for something in the heap, when we pop the maximum value out of our heap, we'll have to flip this around to make it the maximum value again, and we'll have to make sure that we're within our window. So we'll have to check this index. So let's get rid of this. We don't need this stuff anymore. We can simply just grab the top of the heap. Now the top of our heap will always be at index 0. So in that case, we'll say our best option, let's do this here. So our best option will be at heap index 0. I didn't call this heap, I called this max. There we go. Yeah, so our best option will be at our heaps index 0. But again, we're storing a tuple here, so we have to get not just 0, we have to get 0, 0. So we get the top element, which is a tuple with negative result and index. So we'll have to grab the result part out, and we'll have to invert it. So we'll have to set this to negative. But that's only if we have a heap. Otherwise, this will be 0. Okay, so we're going to go through, we're going to grab the best value out of our heap if it exists. If it doesn't, then it'll be 0. We'll add that to our result or our current number. We'll make sure we put this in our heap. Now this is going to be different. This was the append. Now we're going to do a heap push. We're going to push this into our heap, and then we return the result at the end. Okay, now we need to still make sure that this value is within our window. So to do that, we have to do a while. So while we still have some heap, and we'll check the top of the heap. So that's the heap at index 0. And we'll check its index. So that's heap at index 0, 1, because we're storing our result and then our index. So we'll check this index. So is this index within k of our current index? If it's not, then we can't use this element. So let's just see if this is less than our index minus k. That means we're outside the window. We're too far back. We can't use this element. So we're just going to pop it out of the heap and ignore it. So we do a heap q, pop on this heap. So this was a pretty big change. These were a lot of changes. Hopefully it makes sense. We didn't change our initial for loop here. We're still going through every element and saying, what is the best answer we can get if this element were the last element in our subsequence? To do that, we're calling this function, max subsequence, ending at this index. Now previously we used a recursive call to look back and find the best option to add this element to, the best previous subsequence to add this element to. And we did that using a recursive function. Then we changed it to just using a list of our previous best subsequences. So the index represents the subsequence ending element, and the value at that index is the best subsequence that ends at that index. Now, we converted that to a heap to make it more efficient. And so with the heap, instead of storing just the result, we also have to store the result and the index, because the heap will reorder things. So now when we call max subsequence ending at index, we'll have to look at our heap. Do we have a heap? And if we do, is the top of the heap within the range, our k window range, of this current element? So while we have a heap, we'll just check, look at the top element of the heap, and look at its index. If that index is out of the range of this index minus k, so that means that this element came too early, we can't use this element as the last element of a previous subsequence, then we'll just pop it out. So we'll pop that out of our heap. So once we eliminate or pop out all the bad elements from our heap, at that point our best option will be the top of the heap. So we'll grab heap at index 0, and we have to grab the value, the result part, which is index 0 of the top of the heap. And then we have to invert it, we have to flip it around. Again, we have to do this because in Python, min heaps are the default, so we have to make it a max heap by inverting the value. We can only do this if we actually have something on the heap. Otherwise, our best option is just to use this element by itself. All right. Then we'll calculate the result by taking the element and adding the best option to it. We're going to push that result onto the heap. So we do this heap push. We use negative result so that it becomes a max heap, and use the index. And then we'll return the result. Whew. All right, let's see if this works. All right, it works. Let's see if this will pass all the tests. I get a wrong answer. Ooh. Let's use this test case. All right, interesting. We're off by 1, I bet. Let's see, where are we off? Let's see if we can still salvage this video. Okay, let's see, what did we miss? We missed case 5. Looks like our answer was around 6,000. The actual answer should be 11,000. So that's these two positive values, 7,000 plus 4,000 is about 11,000. All right, we're getting 6,000. So we must be including this 7,000. There's nothing with 1,000. So we must actually be including both the 7 and the 4,000, but then also subtracting one of these 5,000s, which my guess would be this first one. Oh, I think that's the problem here. So what we did before with our max subsequence ending at, one of the options was let's not choose any previous subsequence. They might not add anything to this. Let's just choose this element alone. And now this doesn't really have that option here. We're going through, we're popping things off the stack, and we're actually always adding the top of the stack, even if that happens to be negative, which we don't want to do. So let's check this first. Our best option is this, else 0. But we really want to say it's this if it's greater than 0. Oh man, what's a good way to do this? Let's do it this way. Okay, we'll take the top of the stack if it exists, else 0. And then we'll do another check if best option is less than 0. Best option equals 0. Okay, let's see if that fixes our problem. All right, so that fixes the problem. Let's see if we can now pass all the tests. And we pass. All right, let's see. We don't do great. We only beat about 20% for runtime and 24% for memory, so we don't do great with this solution. Now, we can jump in here and take a look at some other solutions. Let's just go to the top. Wow, this is super compact. So let's see, this one's going through, it's keeping track of, oh, it's actually modifying the nums themselves. Now, I generally stay away from modifying the input values because in production code, that is generally a bad idea. Okay, so they're modifying the numbers themselves, they're going through. Once you get your solution implemented and you pass the test, you can jump in here and check this out for yourself. There's a lot of different ways to do this. Oh, let's see. All right, well, that's it for me. I totally went way over time on this one, so I appreciate you hanging in there. I hope you enjoyed this. I hope you had fun. I hope you learned something, and I hope you can go out and write better code.